Okay, last day of equilibrium, KSP. This is not hard. It's just different, ladies. Are you ready to listen? KSP, the SP stands for solubility product, and all the K is the normal K. And so we treat this just like any other equilibrium problem, but we're focused on the solubility of things. So up to this point, we've kind of lied to you. We taught you that silver chloride was insoluble, right? Correct? Okay, so you need to be able to review your solubility rules. You need to know what things dissolve and what don't. The thing about these insoluble solids, per se, they actually do dissolve a teeny, teeny, tiny amount. Not enough to make a difference when we're doing reactions. Like if you do silver chloride, you're not going to be able to tell some of it actually dissolves because it's such a small amount. But there is some math associated with being able to do that, and it's through the use of equilibrium. Anytime we're looking at the solubility of one of those solids, we always write in our RICE tables the solid splitting up into ions. So they're easy to recognize. You always start with your solid, break them up into ions, and then proceed as normal with your RICE table. On the next page here, you're going to have some values. These are KSP values. What do you notice about these equilibrium constants? They're tiny. What it means to be tiny is that it doesn't do a lot of shifting right. So what? Why do we care? If you're tiny, if we're going solid to ions, if they're super, super tiny numbers, which way does equilibrium lie? To the left or to the right? To the left. So it means that the stuff is mostly in solid form. Very little of it will dissociate. Looking at all these, can anyone find the least soluble salt here? Remember, these are all values of KSPs that we're dealing with moles and liters. Now I'm going to go with this one. 1 times 10 to the negative 52. That's not very many moles in a liter. Well, but that's not solubility, sorry. This is just the constants. So basically what you do need to know, the smaller the KSP, the less soluble the substance is. So make note of that. Smaller equals less soluble, which makes sense because products of a reactant, if you're super small, you have tons of reactant, very little product, which means you have tons of solid and very little ions. All right, so let's apply this. We're going to have to, at some point, go back to that table, so kind of keep it around you. So this one says, calculate the KSP for the following salts using the information provided. So we're going to find KSP. We're not going to look at the table. We're going to use the information they give us, do products over reactants, and find the K. So here, because it says KSP, I immediately want you to take your solid in your RICE table and split it into ions. And then we'll talk about what they're giving us. So in this problem, the concentration of chromate in a saturated solution is that value. So what is the solid we're dealing with? Look at the problem. Silver chromate. So Ag2CrO4 is going to be in equilibrium with this ion, so it's 2 silvers plus the chromate. So you're not given equations this time. It's up to you to take that solid and split it into ions. So because this is your solid, we don't worry about it. Because here's the deal with these things. It doesn't matter if you put a kilogram or 20 kilograms in water, the same amount is going to leave based on that KSP ratio. So this is something we don't concern ourselves with. When we start, before dissolving happens, we've got nothing and nothing. So we lose X, but we're not going to mark it. What do we gain here? 2X. We gain X. So on our E line, we have 2X and X. So how are we going to solve for KSP? What did they tell us? The concentration of chromate in a saturated solution, when they're saying that, they're saying after the dissolution has happened, when we're at equilibrium, the concentration of the chromate is 6.5 times 10 to the negative 5th, right? So that is That's X. So now on this side we need 2 times that, so it's 1.3. Is it fourth? Okay, good. 1.3 times 10 to the negative fourth. I just multiplied it by 2. So just like any other K, this time you're going to write KSP though. We're going to have our products, AG plus squared times CrO4 minus 2 to the first, plugging in 1.3 times 10 to the negative fourth. We're going to square that, and we're going to have 6.5 times 10 to the negative fifth, and that's to the first. So to 3 sig figs, what is my KSP? To the negative 9? All right. And luckily, we do not need to put any stuff in there, any units. And remember these numbers, what units do these numbers have? That's not right? Thank you. Sorry, those at home. So what are the units on these things, though? It's in a rice table, so what is X in a rice table unit-wise? Moles per liter. So all of these are moles per liter. If there's pressures in there, there's pressures. But remember, with our Ks, we don't need units on our KCs, KPs, or KSPs. Okay, let's look at this next one. The solubility of silver bromate is 7.2 times 10 to the negative second grams per liter. That's no fun. We're looking for solubility. And I'm going to tell you something. I wish my chemistry teacher would have told me this. Nobody did. And I thought these problems were so hard and scary. I was like, I don't know the solubility. How do you find the solubility? Well, hang on a second. Let's do rice table. What would we do as the next part of the rice table? What do? Next part of the rice table. Split into ions. What does solubility mean? When I say, what is your solubility, what are you telling me? How much have you dissolved, right? I know this is solid, and we put a thing here, but what would represent how much dissolved if we were not having the X here? What would represent that? X. X is how much. That X is solubility. Whenever you see the word solubility, you immediately tell yourself that is X. So if they give you solubility, they're giving you X. If they ask you for solubility, you're solving for X. Don't worry about the 2 or the 3, whatever. It's never going to be 2X or whatever for solubility, because solubility is how much of this guy is leaving. He's always going to have a 1 in front of him. So just find X. Okay? So initially here we have nothing and nothing. It is telling us what X is. So our change is plus X, but we have a problem with the X they gave us. They're telling us the solubility of AgB, they're telling us X is 7.2 times 10 to the negative second grams per liter. What's wrong with that? It's grams per liter. I need moles per liter. So the molar mass of this for every 1 mole of silver bromate, first period got an answer, but I don't trust everybody. What'd y'all get? They got 235, but then I heard all these different decimals, so. $235.76 grams per mole. So my grams cancel, and this gives me then moles per liter. So let's go ahead and multiply that through to 2 sig figs. What is my X, which is equal to the solubility? 2.1 times 10 to the negative 4. 3.1 times 10 to the negative 4. So that's supposed to be our x. So 3.1 times 10 to the negative 4 here, 3.1 times 10 to the negative 4 there. So now we just do our unsubstituted expression, AG plus times BRO3 minus. That's going to be equal to 3.1 times 10 to the negative 4th times that, again, meaning square it. What does our KSP end up being? (9.61), so 9.6 times 10 to the negative 8th. Okay? How do we feel about that? Pretty straightforward? We're going to layer onto this. It's going to get a little more layered as we go through. Okay, so that's one of our simplest ones, finding the solubility. Now to make things a little more mathy, still not hard, but now we're going to use the KSP and find the solubility. If we're finding solubility, what are we solving for? X. So we're going to solve for X. Down here, apparently you guys have a different one. Is it AG2S? All right. So to do these, I'm going to need Ks. So can someone tell me what the KSP for barium carbonate is from the previous page? All right. And then the KSP of silver 2 sulfide? Not silver 2. Oh, my God. Silver sulfide. Whoa. 1 times 10 to the negative 49. Okay. So with these, I'm just doing both of these because they have some issues with exponents and stuff that you need to take a look at. So if I know it's a KSP problem, because they give it to me and they're asking me for solubility, my rice table needs to be my solid, my solid splitting up into its ions. Okay, don't care about this guy. Do I initially have any of this stuff? When they don't say anything, they're just dissolving it in water, so these ions aren't present. There's no common ion effect. So we have 0 and 0. So our thing, we lose an X on the barium carbonate, but we don't care, minus X. Then we have plus X, giving us X and X. This one's pretty simple because all we're going to do now is plug in our X's, plug in our KSP, and solve for X. So our unsubstituted we have 2 times 10 to the negative 9th is equal to X times X. Plugging it in from the E line on the rice table. So X, which is equal to the solubility, just writing that as a note for y'all, is equal to what? Moles, and we need units on this. On solubility, we need units. That's not very many moles dissolved in a liter. I had last period figure it out. It came out to be 0.008 grams is all that could dissolve in an entire liter of solution. And this is not even as insoluble. This is to the negative 9th. Imagine negative 49th. Not much dissolves at all. Okay? Let's set up the next one. I'm only doing the next one just to show you the math. Is there a problem? Did I mess up something? Mm-hmm. They're solids. You don't put it in. It doesn't go into the expression. Correct. Just like in all the other equilibrium problems, if we had a liquid or a solid, we don't include them in the expression. So on this one, again, we're finding the solubility. So we're going to split our solid up into the ions. So it's 2Ag plus plus S minus 2. It's really important you have your 2 in front of that Ag plus, okay? Solid doesn't go into equilibrium. When we start out, since we're dissolving in water, we don't have any contribution of silver or the sulfide ions. So this is a plus 2x. This is a plus x. So here we get 2x and x. So the expression unsubstituted is Ag plus squared S minus 2 to the first. So be careful. Make sure you place the correct thing with the correct exponent. So we get 1 times 10 to the negative 49th equals 2x squared times x. Okay? So do you see how that works out to 4x cubed? 2 times 2 is 4. That's 4x squared times x is 4x cubed. So we get 1 times 10 to the negative 49th is equal to 4x cubed. Now there's multiple ways to do this. You happen to have a cubed button on your thing. You also have the ability to take something to any exponent. I don't like to mess with all that. The way I would solve this, I would divide that by 4. And whatever that is, raise it to the reciprocal, raise it to the third. I do that for everything. It could be the 4th power, it could be the 5th power, so I'd raise it to the 4th or I'd raise it to the 5th. All right? So you need to figure out what way works best for you. You have on your math button, I don't know, there's something that gives you a little like square, and you can put whatever you want in there. On the calculators, I don't. That's actually more keystrokes, so I prefer just less keystrokes. All right, so what do we get for x? Does that sound right? 2.9? And this is moles per liter. That's really small. That's not much of anything that dissolves. So I'm not saying we lied. Silver sulfide's really not soluble. And so when we're doing reaction prediction and things like that, we're not going to see that as something that's going to be in ions. We're going to see that as a solid. Very little that actually dissolves. Okay? All right. So now, we're not going to do the 2 problems on this next page because this is not much harder. So we can cross out the bottom one. I just want to do the top one to make a point. So this time, we're supposed to find the solubility of, meaning we're going to find x, of barium carbonate. But this time, barium carbonate is dissolved not in water. It's dissolved in barium nitrate. So how is this going to change our rice table? Any ideas? Initial concentration. What is barium nitrate contributing that could affect the initial concentration? Barium. So what that barium nitrate is doing, it's contributing barium to that initial line on the rice table. So let's go ahead and set that up. We're still only dealing with the solubility of that solid. So we don't change what we're using in the rice table. And so we're going to get barium carbonate going into its ions. So this time, though, the barium nitrate is contributing what molarity? When this dissolves, for every one of these, I have how many bariums? 1. So what is the concentration then of barium? 0.5. So I have 0.5 here, and I have 0 there, because that barium nitrate didn't contribute any carbonate. It only contributed nitrates. So our change is still plus x plus x. Oh, man. I have to talk about this now, don't I? Okay. So let me preface this with saying that I've been using this analogy for like 10 years. This analogy did not just come about because he's president. Let's just get that out there. But I already have him on the board. You can see how long ago it's been. He was a much younger Trump back here. So this is Trump. Trump's obviously got some money, right? When Trump walks down the street and he accidentally drops a dollar bill, does it change his overall wealth, his overall fortune? No. That's kind of what we're saying here when we say we're going to trump X, we're going to drop X. Right here, this is so huge compared to that particular X. This X is mathematically negligible, and we don't need to include that. So when you do trump X, I want you to write negligible next to it, just to indicate to the reader you know that you're not just forgetting it, that you're saying it's negligible. I call that trumping X. That's going to make the math a lot easier now. So what we're going to do is we're going to say, because we're going to solve, what was the KSP again from the previous problem? Equals 0.5 times X. So let's predict before you do it. Will more dissolve or less dissolve? Well, if we solve for X, that's solubility. Will more dissolve or less? Less, probably, because we've got a huge amount of product here that's taking up that ratio, product space in the product over reactant ratio. So we're hoping to see a smaller solubility. X is equal to what? I'm sorry, louder? 1 times 10 to the negative 9th. 4, it's divided by a half. 4 times 10 to the negative 9th moles per liter. That is going to be the solubility. What was the solubility when we did it in water before, part A on the previous problem? It was 4.4 times 10 to the negative 5th. Wow, that's quite a drop in solubility, isn't it? Okay? So the point of what I'm showing you this problem is the existence of an initial stuff being there. So your I line will not have zeros, and then the ability to trump it. Anytime there's a number next to it, next to an X like that, get rid of the X. Even if it's a 2X, get rid of it. Okay? All right, so we're going to skip B. I don't think we need to do another one of these. We've got enough stuff to do. This is the grand poopah, huge, important point of everything we're doing. Everything we do with KSP is explained to you because all we really want to know in chemistry is, are we going to form a precipitate? After I show you this, you're going to be the all-powerful AP Chem student who can take, I can give you any 2 solutions, and you can tell me if a precipitate's going to form or not. And it's pretty cool. So, to start this, we need to look at what we're mixing and ask ourselves, if a precipitate forms, they're asking, is a precipitate expected? We need to figure out, okay, if a precipitate forms, what precipitate would we make? Look at the 2 and do a double replacement in your head and tell me what the precipitate would be. We're mixing calcium chloride and sodium sulfate. Calcium sulfate would be the precipitate. Why not sodium chloride? It's a big daddy. You've got to know your solubility rules. So if you have to go now and restudy those, do it. Because in this problem, had you done a sodium chloride problem, you would have gotten the whole thing. You got no credit on it at all. You've got to know your solubility rules. So our precipitate in this precipitate in this case would be calcium sulfate. So that is what we're going to do our rice table with. We're going to set up our Ca plus 2 and our SO4 minus 2. So in this, they are mixing some calcium chloride, dink, and some sodium sulfate, dink, together. That's going to be, once they're mixed, those concentrations are the initial concentrations. So even though we don't care about this, we have initial concentrations of both of these 2 things. Can I just put 0.015 in, 0.01 in? No, why not? Well, no. It doesn't matter how much I have. It's 55 milliliters. If I have a 0.1 molar solution and I took 55 mils of it, it wouldn't be 0.1? Nope. Nope. No. You're diluting it. You just did this, remember? Right? We're taking these two concentrations. When we put them together, each of them are diluted. And the dilution point, at that point, that's the initial concentration. So we have to do an MV on each of these guys, just like we did in the post-lab for KC. All right, so our initial molarity, and Isabel brought up the fact there were two. It would have been correct had we cared about the chloride, but we don't. We care about the calcium. All right, but even then, we still need a dilution. Our molarity of calcium in this, because there's 1-to-1, is 0.015, and we're going to use 45 mils of that. What is our new molarity when we get to what's our total volume when we mix the two? 100 mils. 45 plus 55 is 100. So what's my molarity initially of calcium? Folks, please yell it out. I know some of you have it, and this is taking way too long. It's just multiply by two numbers and divide by another. What's the answer? Go ahead. 6.75. That seems really small. Yeah. 0.00. Okay, why was this hard to calculate? It's that times that divided by 100. I was trying to work with I'm not talking about you. I'm saying everybody else. Everyone else is just sitting there. Let's go, folks. So here, this is now our initial concentration of calcium. For the sulfate, for every one sodium sulfate, there's one sulfate. So this means that's the molarity of the sulfate ion. 0.01 times 55 mils divided by, I'm sorry, not divided by, equals the molarity of the new thing we're looking for times the 100 total volume. So what is our new molarity of just the sulfate? 0.0055. So those are my initial molarities. So let me ask you, let's think about equilibrium. If a precipitate forms, which way would this reaction shift? To the solid, left. If a precipitate doesn't form, which way it would shift? Right. So we need to figure out which way it shifts. How do we figure out which way something shifts? We have the K. What is the K? We do need it. Somebody look up calcium sulfate's KSP.
3 e to the negative 5.
How does the K tell us? How do we find if something shifts, guys? We've already done this. Okay, y'all are saying less than 1? Seriously? If we had a zero, if we had all equilibrium stuff and we wanted to figure out which way something was shifting, you're telling me you're looking at the K? What do? You find Q. And what does Q do then? If Q is less than K, it'll shift one way. If Q is greater than K, it'll shift the other. First period got y'all on that. I'm a little shocked. Do we understand? We have to determine the direction of shift. That's the point of this problem. If it shifts left, we know solid is formed, so that means, yes, a precipitate will form. If it shifts right, no precipitate. So let's go ahead and find Q. Q is equal to the same products over reactants, and since the solid's not in it, we just do the two concentrations times each other. They're both raised to the first power. So what is my Q? 3.71 times 10 to the negative fifth, and the K was 3 times 10 to the negative fifth. So what's my relationship? Q is greater than K. So Q needs to get smaller. Knowing that this is product over reactant, how do we get smaller? More reactants. What is more reactant? Left shift. So what does that mean? Yes, precipitate forms. So if you were to mix 45 mils of 0.01 molar of calcium chloride and 55 mils of 0.01 molar sodium sulfate, you would make a precipitate. All right? Do I need to restate any of this? Do we understand? So when you're given a problem like this, you need to show me your Q and show me your Q comparison. You can't just say, because the problem that ultimately is asking, is there a precipitate? So theoretically, your answer is yes or no. But that's not going to, even if you said yes correctly with no work, you're not getting any credit for that. You have to show the work. Okay? All right. Now we're going to move on to an AP problem. This is our last problem of the day. This problem is all-encompassing. It's from an old exam, and it's a very good problem. And if you can handle this problem, you're going to be great with KSP. You'll be fine. So here, it gives you a system, and it says, in a saturated solution, MgF2 at 18 degrees, the concentration of Mg plus 2 is 1.20 times 10 to 1 times 10 to the negative third. The equilibrium is represented above. So do you kind of see already how it's a KSP problem by the way they did the solid going into the ions, right? Even more, Part A says write the expression for the solubility product and then calculate the value of KSP at 18 degrees. So we're going to treat this just like we've done, and we're going to first write the expression. So what is the expression? What is KSP equal to? Concentration of Mg plus 2 times F minus squared. That's the first point of the problem. You would get a point for that. Now, because we wrote it here, I'll never require you to see it again in your work if they specifically ask you for it, because you can always go back and reference it. Okay? Now, the next part of A says, and calculate its value. So to calculate the value, I'm going to put in my little rice table. Now, you get to a point where you can maybe do it in your head to the extent of knowing where to put X and all that kind of stuff. I don't think anybody really is there at this point, so I'm going to continue to want you to set it up. So originally, we have none of this. This is a plus X. This is a plus 2X. And so X and 2X goes here. Now, what did they give us in the actual introduction that would be useful? The solubility or the concentration of Mg plus 2. So they gave us X, right? So 1.2 times 10 to the negative third is X, and 1.21. And then 2.42 times 10 to the negative third is fluorine's concentration at equilibrium. So now how do we solve for the KSP? Plug it into the expression, which we already have. So we do 1.21 times 10 to the negative third times 2.42 times 10 to the negative third squared. Bless you. So what do we get?
6.9.
Can I get a second on that? 7.09. That could just be a rounding thing. Who knows? So that's equal to our KSP. All right, so that's part A. Got it? Questions on A? All right, let's look at B. Calculate the equilibrium concentration of Mg plus 2 in a liter if to which 0.1 moles of solid Kf has been added. Kf dissolves completely, assume the volume change is negligible. So what they're saying is if we're putting 0.1 mole of Kf in a liter and the liter's not changing volume, what's the molarity of the Kf? 0.1. Okay, so they're basically giving us similarity to KF. So what we're done here is we're shifting the equilibrium, but now we have what we call the common ion situation. So how is our Rice table going to look different this time? It has a starting concentration of what? Which one is affected? F minus, because we're adding KF, so that's going to now be, that 0.1 is now our starting concentration of F minus. Now students say, why don't we multiply it by 2? No. The person that stressed the system out put 0.1 moles in there. They didn't put 2 moles in there. They put 0.1 moles in there. So that's what you put here. That's the concentration in the flask. We have none of this yet because we didn't add any initially. So here we have a plus x and a plus 2x. So on our E line we have x and 0.1 plus 2x. What can we do? We're going to trump this guy and say negligible. Negligible. And so our KSP, we already have our thing up here. Oh, we're actually solving for, I'm sorry, I should be telling you, we're looking for this concentration, right? Calculate the concentration of this. So we need to know the KSP. Do we know the KSP at 18 degrees in order to solve for x? Didn't we just find it? Yeah, this was it at 18 degrees. So we're going to take this guy and set it equal to 7.09 times 10 to the negative 9th. That's equal to the concentration of Mg plus 2, which is what we're looking for, which is x, times 0.1 squared. So take 7.09 times 10 to the negative 9th divided by 0.1 squared. Now we're either going to get 11 or 7, I never know, as our exponent. So 7.09 times 10 to the negative 7 moles per liter. So did our magnesium concentration drop? When we had nothing initially, it was 1.2 E negative 3. Throw in some KF, it drops to 7.09 times 10 to the negative 7. So that makes sense. Okay? All right, 2 more parts. Predict whether a precipitate will form. When you see that, you need to be thinking dilution Q, dilution Q, dilution Q every time. So will a precipitate form? We're going to need to figure out, compared to that K that we have, whether or not we get a shift left or right. So the K was what, 7.09 times 10 to the negative 7? I don't remember the exponent. Negative 7? Okay. All right, so this is our KSP. Negative 9. Okay, so that's the K. So what do we need to do first, though, in order to figure out initial concentrations? They told us a concentration of MgF2, they told us magnesium nitrate, how much and what concentration is mixed with sodium fluoride. So we're going to make magnesium fluoride if it's going to precipitate. Magnesium nitrate contributes to the magnesium, sodium fluoride contributes to here. So our initial concentration of magnesium nitrate, for every 1 magnesium nitrate, there's 1 magnesium, is 3 times 10 to the negative 3rd. We're mixing 100 mils of that. What's our total volume? 300. So what is our concentration of magnesium plus 2? It's a third, 1 times 10 to the negative 3. It has to be, because it was 100, then it's 300. That's got to be a third of 3, which is 1. All right. 2F, I won't be able to do this one in my head. We have 3 sorry, 2 times 10 to the negative third molar, and it's 200 mils of it. What's its new concentration at a total volume of 300? So what's my F concentration? Just someone tell me. 0.00133. I'm assuming that's right. So now we know our concentrations. We got to figure out if precipitate forms. What do? Find Q to figure out direction of shift. We already have our expression that you can go back and refer to. 1 times 10 to the negative third to the first times 0.00133 squared. So Q is equal to 1.769 e negative 9. So Q is less than or greater than K. Q is less than K. Q needs to get bigger. Do we need more products or more reactants? More products. So we're going to shift which way? Shift right. Precipitate or no precipitate? We're shifting toward the ions. No precipitate. So you've seen one of each now. Okay? Part D, love this. This is the sexiest problem on the planet. I love this problem. At 27 degrees Celsius, the concentration of Mg plus 2 is in a saturated solution is 1.17 times 10 to the negative third molar. Is the dissolving of this stuff endothermic or exothermic? Explain. Take a second and then see if someone can tell me. Go ahead. But do we have? Okay. We really don't have to calculate anything, though, to find that. He's correct. We want to see which direction adding heat is going to make this shift. But we've got enough information without doing a calculation. What do you think? Let's do that. Mg plus 2, when it's 18, what was its concentration? 1.2 times 10 to the what? Negative 3. All right, and just to remind you, that's what we're dealing with. What is the concentration then at 27 times 10 to the negative third? As we added heat, which way did that shift? To the left. Where do we write the word heat? So when we increase it, it shifts left. Plus heat. So that makes this exothermic. I'll repeat it. This is sexy as hell. When we went from 18 to 27, this concentration of this guy decreased. So as we added heat, it shifted left. Temperature went up, right? 18 to 27. As we had added heat, it shifted left. Where do we write the word heat, reactant or product, so that when we increase it, thinking of Le Chatelier's principle, it would force a left shift? Over here. We go up from 18 to 17, increasing, shifts left, decreasing the concentration of that. So it's exothermic. You cannot tell me that's not cool or hot because it's exothermic. You can't tell me that's not really interesting. The way things come together. Okay, we're putting now directly, thermo directly with equilibrium. Okay? All right. That is all. That's all for the